So as far as what a normal force is or how it is calculated, what I want to start with is the fact that a normal force is really a pressing force. It's the force that presses one surface into another, not through it, just so they are in contact. So anytime any two objects are in contact, a normal force will be produced. The size of the normal force depends really on what's called the ultimate strength of each surface. In that each surface, because of its atomic makeup, can withstand a certain amount of force before it will break or deform. And that's going to get into a lot of engineering concepts. So let's just say, for the sake of argument, we are never going to have a surface that is going to break. So the normal force that a surface produces will always prevent an object from passing through that surface. A normal force is also another way to say perpendicular. So if you have a contact surface between two objects, the normal force is going to be the force that the surface pushes up on the bottom of the object. If we take this as being the surface, where the block is on the tabletop, the normal force is always going to act perpendicular, so it's going to point up or vertical because it's going to push on the bottom of the object. So it just means as long as you know what your contact surface is, it's going to be directed perpendicular to that surface. Key point right here. The magnitude of the normal force is equal in size but opposite in direction to the sum of the forces pushing that object against the surface. So it doesn't have to be equal to the weight. Basically, you want to look at the ups and the downs and then look at the size of the normal force. And if there is no net motion, no net acceleration, then we know that the sum of all the forces acting have to sum back to zero. And so the normal force, because it can resist with an infinite amount of strength as far as we're going to consider it, it can always resist against any forces directed against it or opposite to it. So it's a balancing force. It adjusts so that you have no motion through the surface. In the simplest case that we're going to look at in a second, the normal force value is equal in magnitude but opposite in direction to the weight, because we have to have a net force of zero in the vertical direction, and the normal force will oppose with whatever it needs to counter the gravitational force. So the last little piece of the puzzle here, the weight and the normal force are not always equal and opposite. That is a special case. And so that's the first one I want to look at right here, is if we assume that an object, this block, if we say that this is 10 newtons down, so it's a 1 kilogram, or 9.8 newtons down. If I tell you this block is at rest on the tabletop, I know that the reason the block is not passing through the tabletop is because there's a tabletop there, and the tabletop has inherent strength to it. And so what it's going to be able to do is it will resist with a certain amount of force in the other direction, saying, no, you're not going to come through me, I'm going to resist. And this will, by default or by consequence, because it's not moving, the result is the normal has to be equal to 10. So this is a case where the magnitude of the normal is equal to the magnitude of the weight. That's the case we really focus on here in this class. However, I do want to look at a couple of other instances. Let's take a look at this case. What if I push down on the top of this box with, say, 20 newtons? And we know that the weight of this box is 10 newtons. So it's a downward pull by the earth and a downward push by me. We have a net downward of 30 newtons, correct? Well, if I'm just pushing on the box and I don't push it through the table, I'm not that strong, then the table's not going to move up or down, which means that the sum of all these forces has to come back to a net force equal to zero. So what that's going to mean is the normal force, because you're pushing down against the surface with more force, the normal force will say, well, I can give an infinite amount of resistance to that. The normal force now is 30 newtons because we have to add all these up and get 0 back for the net force. Notice, the weight of this thing is 10 newtons. The normal force produced by the surface is 30. So if you add any other downward or upward vertical forces, the normal force will adjust to balance so that the object does not move up or down. Let's take a look at the last case, just so I can make my point here. If we look at a refrigerator magnet that is stuck to the side of a refrigerator, because it's a refrigerator magnet, the weight of that magnet, I don't know, it could be a really small amount. I'm not going to say it's under a Newton, absolutely. Now the normal force here, remember, the magnetic pull between the refrigerator and the magnet is going to pull these guys together. And if we look at what's going to happen, the magnet's not going to pass through the surface of the refrigerator door, so it's going to resist with a force that is perpendicular to the contact surface. So it's going to be produced, and it's going to be oriented this way, because it's out of the surface perpendicular. If the magnet does not fall down or slide down the refrigerator door, it's safe to say that the weight pulling down is matched by another force that is up. But that up force is not the normal force. It's actually friction. It's preventing the sliding motion. But what I'm looking at here is the fact that this normal force, if it is clamping or pushing against the bottom of this magnet, it's going to be fairly significant as far as the normal force, because it's going to work with friction or in conjunction with the coefficient of friction to stop this thing from moving. So the case here is basically the normal force can be any value, doesn't have to equal the weight, special condition, special situation, and the normal force doesn't even have to be opposite to the direction of the pull of gravity. Okay? All right. What I'd like to look at now is what's called the coefficient of friction. It's an assessment of how resistive two surfaces are to sliding over one another. And the value, the higher the coefficient, the more resistive it is to that sliding. It's a quantity that was developed by scientists that were trying to figure out how do we talk about the, quote, stickiness or resistiveness of a surface. So it's an empirical relationship. It's going to be looking at how much force it takes to pull something along and keep it moving at a constant velocity. And that way we can look at the frictional force that is resisting that pull, which is the basis for the friction lab. If we just look at the numbers, large numbers are more resistive than small numbers, we can look at the table here. And what I want you to notice is, depending on how we address friction, there's what's called static coefficient of friction and kinetic coefficient of friction. And this is mainly due to the fact that when surfaces are not moving relative to another, it usually takes a little bit more pulling force to get an object to move than it does to keep it moving. And that comes back to the coefficient value actually is a little larger when the surfaces are stationary and you try to move them. So I kind of view this as my locking. This is going to be the coefficient you're going to use to figure out the locking force. In other words, if you can't unlock this surface or these surfaces, you're not going to move the object. If we look at this column, this is the friction that is produced when the things are sliding. So just keep those two things in mind. And you can see in some instances these values are fairly close, but in other areas they're fairly spread apart. And that is due to the actual roughness of the surfaces. It's due to the bonding or the atomic makeup of that material. So you really got to check it out and test it to figure out what's going on here. If I look at a couple of examples here, if you take like an automobile tire on dry concrete, if they're decent, you're going to get a static coefficient of about 1.0, kinetics about 0.8. So when the car is sliding and the brakes are locked up, that's the 0.8. Okay, when the tires are rolling and you're not spinning them, you're 1.0. If you're using racing tires, something specifically designed to have a lot of grip, you could have coefficient of friction values above 1.0. Sliding, I don't know. If we start to work down the table here, what I want to look at is when you're doing any skiing or snowboarding, you're probably looking at a static coefficient of friction or kinetic of about 0.1. And again, this will depend on what's the base wax, what are the snow conditions. But you can see it's fairly low because you want to slide down the surface. So the lower the coefficient, the more you're going to be able to slide, less resistance. Teflon, which is a material that was accidentally discovered and then marketed to the cooking utensil end of product development and is used in medical applications. Pay attention to this. In every single case here, except this one, which is my mistake, the coefficient is always determined based on the two surfaces in contact. So Teflon on Teflon, wax wood on snow, dry bake pad on steel. So you can't have a coefficient of just wood. It's got to be what is the wood sliding against. So this should be up in the top, should be racing tires on concrete, but it isn't. So I made a boo-boo here. If you look at brake pads, I'm going to kind of focus on this. These aren't very big numbers, the coefficients. They could be a lot larger. But when you have a brake pad that is stationary on a wheel and a rotor that is moving, you're kind of looking at the kinetic coefficient of friction because as you hit the brakes, the wheels haven't stopped yet. So you're about 0.13 on the coefficient, which means it's not going to be a massive amount of roughness between the surfaces, but there's other ways to get more friction from that. The little diagram here is showing you the fact that when we look at the surfaces in contact, if one is sliding relative to the other, oftentimes we talk about this as surface roughness, which I'm showing here by the, quote, hills and valleys or the highs and lows that are really impeding the motion of the surfaces. And when these surfaces slide past one another, they knock off the high and low points. And so you get more wear and you produce heat, and that allows things to slide. Last couple of examples here. If you have a race car in particular, anything that's designed for high performance, high speed, and aggressive braking, the braking system on a car is primarily made out of metal. It's going to be an alloy, and the brake pads are going to push against a rotor, which is a disc. And the frictional forces get so large that you make the metal glow. Okay, that's a solid piece of metal in there, a disc. And when you start to see metal glowing, you're in the 1,000+ Fahrenheit temperature range on that. So you're generating a lot of heat. If you need to get a hip, shoulder, any kind of a sliding or gliding joint replaced in the body, the material they're going to use is not going to be as good as what the human body produces. So you might have a material that is a ceramic, or it might have some Delrin or Teflon. But the wear resistance on these, you can get 15, maybe 20 years out of a joint before it needs to get replaced. So it's going to wear out. Quick story on these tires here. These used to be on my Saturn when the Saturn cars were produced in the mid-90s. And that summer I was doing a lot of driving to Maine, and my gas mileage is going up. Every time I put a tank full in, I'd kind of check the mileage. I was getting about 270, 280 miles on a tank. Middle of the summer, I was 300, 305, and I think I got up to a little over that, and I really didn't pay attention to the car that much, so I didn't know that the quality of the tires were what you're seeing here. The thing that prompted me to really look at this was I was in a really bad rainstorm coming home one night, and I'm driving, and the car decided to switch lanes on its own, and so the car was hydroplaning, which means you had a layer of water between the treads. The treads weren't deep enough to channel the water. So very, very low friction, but the car did not have a lot of grip. And I decided to look at the tires, and this is what I saw. And so, yeah, I took down the resistive force of friction that allowed me to have traction that also caused lower gas mileage. But when that friction got reduced, I got increased mileage, which is great. But if you need to steer or decelerate the vehicle, it wasn't that good. So again, there's a trade-off here. Friction is traction, but it also causes resistance and drag. So that's going to be it for this lecture, guys. This should be a good intro to let me start working with the friction equation. So have a good day, take care, and I'll see you next class.